Hi everyone, welcome to this first in a series of bonus tutorial sessions for the HSMA programme, where we take you through some of the additional concepts that we didn't have time to cover in the main training. Today we're just going to do a short tutorial on sensitivity analysis, which is something that we didn't have a chance to talk about in the first session, but which is really important when we're thinking about building models. So we talked a bit about validation and verification and the importance of both validating and verifying models. Another really important consideration to make whenever we build any models is to think about the uncertainty around our parameters. So what do we mean by that? Well, let's imagine for a moment that we wanted to use a normal distribution to represent a process time in our model, whether that's, for example, seeing the triage nurse or time being registered at the reception desk, whatever it might be. Now, it's worth saying it's very unlikely that you'd use this distribution in reality for a process like that, but for the purposes of this demonstration, it's a good way to demonstrate it. So let's imagine we're using the normal distribution. Now the normal distribution is defined by two parameters, the mean and the standard deviation, and if we have both of those, then we can define a normal distribution. Now the mean and standard deviation that we're going to use for our normal distribution is going to be derived from whatever data we want to plug in. Now the data that we've got in the vast majority of cases is only going to be from a sample of data. We're not going to, for example, if we're looking at triage time with a nurse, we're not going to have data about all triages that ever have and ever will happen, and so it's only ever going to be a sample. But there's a problem with that, and that's that any time that we make an estimate from that sample, i.e. the mean or the standard deviation, there's inherent uncertainty, because our sample mean might differ from the true population mean, for example, because of chance, because of the particular sample that we've taken. We may take a sample, for example, during a particularly unusual period in the historic data, or it might be because the sampling process itself is either unreliable or biased, that we've only taken it from good months in the data, for example. So in other words, if we were to repeatedly resample, say, treatment time data from our real-world data, the mean would differ slightly each time. And so there's uncertainty around the mean, standard deviation, whatever parameters we need to define for our particular distribution. So what do we do about that as modelers? Well, the gut instinct may be to say, well, can't we just take a bigger sample? Well, that's not always possible. It might be that you're using a sample that represents all of the data that either you have or which is going to be representative for what you need. And even if you could, well, it helps, but it's not going to eliminate all uncertainty. It's also not going to help if the sampling process is biased in itself. And there may well be longitudinal issues, particularly in healthcare. This is really important. As you probably know from your own experience, processes change all the time, and so, you know, if we were to take data from 20 years ago, it's unlikely to be representative of what's happening now. So another way we could try and tackle this is to estimate the uncertainty using sample statistics, and there are statistical approaches that can help us with that. But a really good way of trying to handle some of this parameter uncertainty when we're modelling is to do something called sensitivity analysis, and that's basically where we make small to medium-sized changes in a parameter value. So let's say it's the mean. Let's say we've estimated that the mean time that someone spends with a triage nurse is 5 minutes. We make small changes to that, and we see what happens to the results. And if we get really big differences from these small to medium changes from that parameter, then we know that that parameter value is very sensitive. In other words, the results are very sensitive to us being wrong. So if we were to change, for example, 5 minutes to 6 minutes, and then we get a massive difference in the results, then that's worth knowing, because actually it means, well, if we're wrong about it being 5 minutes, and actually if we knew what the true population mean was, and it was 6 minutes, then those results would go out the window, and in fact they'd be hugely different. So that gives us a real insight into what the results are sensitive to. And it can also work the other way. So if we make a small to medium-sized change, or even a large change, and actually there's very little difference, then we can be confident that it doesn't matter if we're a bit uncertain, that we're a bit wrong with this parameter value. It doesn't matter, because actually it's not going to change the results that much. So let's take a look at an example. So let's bring up the model that we were running during the first session. So this is the model of the emergency department. So here we are, and we walked through a little bit of this model. As I say, you're going to actually learn to develop this model later on in the course. So if I scroll down here, we've got a section here where we define the parameters for the distribution. So we've got mean inter-arrival times. These are all in our time units are effectively minutes, so there's 8 minutes here. Registration time, average registration time of 2 minutes. Mean triage time of 5 minutes, and a mean treatment time of 30 minutes. So let's, for example, first of all, let's start with the registration time. Let's run it in the base case so we can see what we're doing. So let's just run that model. Now, in reality, you would want to run this model lots and lots of times and take averages over those results. Just for the sake of speed, we're not going to do that here. But I've run that once and see the average time in the system's about 147 minutes. I'll just run that a few more times so we get a sense of what the results look like. So about 150, just run it once more. And 160, so it's floating around the sort of 150, 160 mark. So let's change now the registration time. Let's say we were wrong about the registration time, and in fact the average registration time, if we knew all of the registration times, is actually 3 minutes, for example. So it's actually a minute longer than we thought. So let's just run that model again and see what happens. So 140 minutes. So actually, it's not a huge difference. It's about the same as we're seeing before. In fact, that's likely to be a natural variability. Again, we're getting just under 150, the same as we were before, because actually we're lengthening the registration time. So it should, if anything, make the timing system a little bit longer. But it doesn't seem to have had a major impact on the results. Let's set that back now, and let's try changing the mean inter-arrival time. So at the moment we've got patients arriving into the ED every 8 minutes. Let's say that they arrived a little bit more frequently than that. Let's say they actually arrived every 7 minutes. Let's see what difference that would make to the results. Again, it's only a very small change. It's quite possible that we're out on the mean by a minute if we knew what the true population mean was. So let's run that and see what happens. My goodness, look at the impact that's had on the system. So suddenly we've got an average time in the system of over 18,426 minutes. That's a huge difference to what we're seeing before. Now, of course, it could be an extremely bad run of bad luck. So let's just run that again, see what sort of results we get. No, seems to be the case. So it looks like actually the results are hugely sensitive to the inter-arrival time. And if we've got that initial estimate of 8 minutes, even slightly wrong, all of our results from the model can go out the window. So that's really important to know. Now, it may not be that we can do anything about that other than to report that in our results when we're giving our results in the model. It might be we simply have to say, well, look, here are the results, but having done sensitivity analysis, we also know that the results are highly dependent on the accuracy of our estimated inter-arrival time. And if we're even slightly wrong on that, then it's going to have a huge impact on results. Let's try going the other way. Let's see what happens if we run it with 9 minutes. And similar again, so we can see, look, we were getting about 150, 160 minutes before, and actually that's gone down quite a bit because, of course, a longer inter-arrival time means patients are coming in less frequently, and so it's had quite a big impact just from a single minute being out by a minute. So that's really insightful for us and really important and really worthwhile to do that sensitivity analysis. So there's also other ways in which we might have uncertainty, other types of parameter uncertainty. It may not just be the value itself that we're using. So in the case of the normal distribution, for example, normal distribution, say, takes 2 parameters, the mean and standard deviation. So we've already seen in the case that it might be that the mean either is an overestimate or an underestimate. It might be that the standard deviation is also an overestimate or underestimate, i.e. there could be a higher or lower spread of process times than we've accounted for. Might also be, let's not forget, another type of parameter that we're putting in our distributions is the distribution itself. We're making an assumption about the distribution that is going to best represent the variability within our data. And I can tell you now, if you're assuming the normal distribution for things like treatment times, you're using the wrong distribution. But nonetheless, it might be that we're using completely the wrong distribution. And so here we see an example. These two distributions have both exactly the same mean, but there's a completely different shape to the curves. So it's really important to think about all sorts of parameter uncertainty whenever you're developing your models. Models are filled with uncertainty and unknowns. What's really important though is to get a handle on that and to make sure that our results are reported in context, and that we've explored that uncertainty and we have some sense about the impact that uncertainty may have on our results, but also thinking about whether, for example, our results may be underestimates or overestimates, depending on where we think we might be making assumptions and how that might be influencing the data and the results that we get. So I urge you to consider sensitivity analysis for your own models as you carry on with your projects. And to bear this in mind, because it's a really simple but a really powerful way of getting a good handle on parameter uncertainty and what it means for your model. Hope that tutorial was useful. If you have any questions, please contact us, let us know. Otherwise, we look forward to seeing you in the next tutorial. Goodbye.